Hello, my name is Jason Adrians. Today is 3/28/2025, and this is my Unit 2 presentation, a genetic mapping demonstration. So today I'm going to be walking through the data that was given, and from that data that was given, determine the correct placement of genes relative to one another and their map distances. Some key terms that I'm going to be discussing throughout this presentation and that are important to know what I'm talking about beyond this point are recombinant classes or single crossovers, double recombinants or double crossovers, the coefficient of coincidence, and interference. Recombinant classes are essentially, simply put, you have parental classes, those parental classes cross over single or once or twice, and that's a single crossover or a double crossover respectively. And then the crossovers create recombinant classes, and those recombinant classes are just an order, the different order of those genes that from the parent, from the parental classes. The coefficient of coincidence compares the observed number of DCOs to the expected number of DCOs, and then interference basically takes the likelihood of one crossover event, and determines the likelihood of another one occurring nearby. So this is just the data that was given organized into a table, and there's a few analytics that you can get from this. Assuming that these are all offspring, the highest frequency are going to be the parental classes, because a crossover event is a very rare event in the first place, and a double crossover event is even more rare. So the highest counts are going to be ones that have zero crossovers, which are just the parental classes. And the highest counts in this data are +++ and ABC. So I assume that these are the parental classes. From that, then all the other ones are some form of recombinant class, either single or double. And there is a way to tell the difference. The middle gene, if the middle gene only changes, then it's a double recombinant class. If any other gene changes and it's only just one, then it's a single recombinant class. So for example, you might expect, based on frequency, that a double recombinant would be the lowest frequency, which sometimes is the case, but not always. And in this data, the +B+ is the double recombinant, and the A+C is the double recombinant. And I touch on this in the next slide here too. That's the double recombinant, which means that every other one's a single recombinant except for the parental classes. So if you assume that these are the parental classes, +++ and ABC, and then +B+ is the double recombinant, and then A+C is the other double recombinant, then every other one's a single recombinant. So A++, ++C, +BC, and AB+ are all single recombinants. So moving on to the calculations, the first thing that is I just totaled the number of offspring, which came out to be 5,742. This number is going to be used throughout a lot of calculations. That's the first thing that I did. Then I calculated the distance between the A gene and the B gene. So in order to calculate the distance between the A gene and the B gene, you have to total up the frequencies that occurred. There's the crossover event that occurred in between the A gene and the B gene. So the double crossover events had, or the double crossovers had a crossover in between the A gene and the B gene, and then the single crossovers that just had the crossover in between the A gene and the B gene. So that was the A++C, and then A++ and then ++C, which are the 100 and 140 totals respectively. Then that total came out to be 1060. 1060 divided by 5,742 to get 0.1846, multiplying that by 100 gets 18.46 centimorgans. So that's the distance between the A gene and the B gene. Then the distance between the B gene and the C gene is the same thing. You take the total counts that had a crossover event in between the B gene and the C gene, which is the two double crossover events, plus the allele frequencies that had a crossover event just between the B gene and the C gene, which came out to be 1010 and 970 respectively. So this totaled to 2,800. 2,800 divided by 5742 to get 0.4876. Multiplying that by 100 equals 48.76 centimorgans. So that's the distance between the B gene and the C gene. And as you can see, so this is the final map of that. So this is like a physical distance between the A gene is 18.46 centimorgans, then the B gene occurs, then there's a physical distance between the B gene and the C gene, and that is 48.76 centimorgans. So that's the final map that occurs. Moving on to the coefficient of coincidence. The coefficient of coincidence compares the observed number of double crossovers divided by the expected number of double crossovers. So you have to first calculate the number of expected double crossovers. So the expected number of double crossovers, you take the two percentages that are calculated in between the A gene and the B gene and the B gene and the C gene. You multiply them to get, it can be thought of as 0.9% or 9%, 0.09 or 9%. And then to figure out what 9% of the total is, you have to multiply that. So 9% of 5,742, it comes out to be 516.78. Then the observed number of DCOs is 820. So that's just the frequencies. Hang on, I'll show back. The frequencies of plus B plus is 400, and then A plus C is 420. So that's 400 plus 420 is 820. That's the observed number of DCOs. The expected number of DCOs is 516.78, and then you divide the two, and that comes out to be 1.59. Then the interference, you take 1 minus the coefficient of coincidence, and 1 minus 1.59 is negative 0.59, and that's just the likelihood of a crossover event occurring right after another crossover event, right after the next gene. So that's what that calculation shows. Beyond this, there's the final map that I already discussed, and thanks for listening.